Welcome to our podcast. In this episode, we explore how AI confirms 50 new exoplanets in breakthrough discovery. In a groundbreaking first, British researchers have identified 50 new planets using artificial intelligence. A research team led by David Armstrong at the University of Warwick in the United Kingdom created a machine learning algorithm and trained it using data on confirmed planets and false positives from NASA's retired Kepler mission. The scientists then used the algorithm on a dataset of still unconfirmed planetary candidates from Kepler, resulting in 50 new confirmed planets, and the first to be validated by machine learning. Their results were reported in a new study published in the monthly notices of the Royal Astronomical Society, where they also performed the first large-scale comparison of such planet validation techniques. Previous machine learning techniques have ranked candidates, but never determined the probability that a candidate was a true planet by themselves, a required step for planet validation. These 50 exoplanets range from worlds as large as Neptune to smaller than the Earth, with orbits as long as 200 days to as little as a single day. By confirming that these 50 planets are real, astronomers can now prioritize these for further observations with dedicated telescopes. The algorithm we have developed lets us take 50 candidates across the threshold for planet validation, upgrading them to real planets. We hope to apply this technique to large samples of candidates from current and future missions like TESS and PLATO, Armstrong said. In terms of planet validation, no one has used a machine learning technique before. Machine learning has been used for ranking planetary candidates, but never in a probabilistic framework, which is what you need to truly validate a planet. Rather than saying which candidates are more likely to be planets, we can now say what the precise statistical likelihood is. Where there is less than a 1% chance of a candidate being a false positive, it is considered a validated planet, added Armstrong. Probabilistic approaches to statistical machine learning are especially suited for an exciting problem like this in astrophysics that requires incorporation of prior knowledge from experts like Dr. Armstrong and quantification of uncertainty in predictions. A prime example is when the additional computational complexity of probabilistic methods pays off significantly. Dr. Theo Demoulas, from the University of Warwick Department of Computer Science, and Deputy Director, Data-Centric Engineering and Turing Fellow at the Alan Turing Institute, said, "Once built and trained, the algorithm is faster than existing techniques and can be completely automated, making it ideal for analyzing the potentially thousands of planetary candidates observed in current surveys like TESS." The researchers argue that it should be one of the tools to be collectively used to validate planets in future. Almost 30% of the known planets to date have been validated using just one method, and that's not ideal. Developing new methods for validation is desirable for that reason alone. But machine learning also lets us do it very quickly and prioritize candidates much faster. We still have to spend time training the algorithm, but once that is done, it becomes much easier to apply it to future candidates, Dr. Armstrong said. You can also incorporate new discoveries to progressively improve it. A survey like TESS is predicted to have tens of thousands of planetary candidates, and it is ideal to be able to analyze them all consistently. Fast automated systems like this that can take us all the way to validated planets in fewer steps let us do that efficiently, added Dr. Armstrong. Thank you for listening to our podcast. We have many more such compelling episodes for you. Enjoy them. Do share your opinion in the comment box and subscribe to us for more.